Okay, so you all, are we on?
Yeah.
Sergio, are you there? Hello, Sergio. So you're all understandably getting tired of Markov chains, and some people aren't showing up, in fact. So I'm going to, like in the next, today and maybe it'll spill over into Tuesday, I'm going to knock off part one of the course on Markov chains. Okay? So just as a recap, oh no, we might be in trouble. Oh no, the pen, we don't have a pen. We might be in trouble. Yeah, Swang, thank you. Maybe two dark ones. So we had this, and I gave you most of the proof from this comparison theorem. Comparison theorem. And actually, I'm writing down a slight extension of what I proved last time. So I eliminated that in the lecture last time, and I'm sticking it back in now, mainly to emphasize the fact that actually this comparison theorem doesn't require that you assume the tau is finite valued. It's really used to prove the tau is finite valued. So you can actually keep that in there. And then the trick is to apply this to get this. You take G to be this indicator function, and that takes a bit of work to show that if B is just a constant times the indicator function of a bounded set, a finite set, then this is actually uniformly bounded in X. And so I gave you a homework assignment to sort of help you think about why it's almost obvious it should be bounded when this is a finite set, even for an unstable Markov chain. Because if it's unstable, that's right, and this is a return time here. If it's unstable and tau is a time to hit some state, well then you shoot off to infinity, you've never seen anything, but you're also not seeing that finite set, so you get just summing zero. You know? So this is with an indicator function of a set, this thing is uniformly bounded, whether it's stable or not. That's a really useful trick. If you're going to do research in this area, and I know that's only 10% of you. So anyway, so you all should know why this is important, right? Because this is what, we had a representation of the invariant probability mass function, and it was based on that. And so once you get this, you've got all sorts of nice things. So today, I want to knock off the important parts of these nodes. So there's a hell of a lot to do in two and a half hours or something like that. But I'm not going to prove everything. I'm going to give you the main ideas. So there's a bit of a discussion on converse theorems. I'd like to be able to go the other direction. So if a drift condition like this holds, then this is finite. Well, the converse turns out to be easy as well. And for the same ideas, we get a representation of Poisson's equation, which is really much more useful than the other one. And then there's this idea of coupling, which is really valuable for understanding simulation, ergodic theory, everything. You'll hear talk about coupling all the time in statistics and machine learning. Yep.
So last class I had asked the significance of B3, and so I understand that. Now we have the comparison theorem. We're looking for converse theorem. So is it all linked back to if you have some problem and you're trying to show that you have an invariant distribution, and you want to know where you can start to kind of show that? Is that the reason? Like, what's the utility of the comparison?
Okay, let's do this. I'm not going to write down. So, step one, this is valuable because I'd like to be able to say that, like an accountable state space, does an invariant probability mass function exist or not? It's like the MM1Q, if the load is less than 1, we have an invariant probability mass function because we can write it down. It's geometric. And if the load is bigger than 1, if you just look at the sample paths, they shoot off to infinity. But for more complicated models, if like M1Q, if the arrival process had some exotic distribution or something, you could just go through and get this inequality. No, this is true. Probability mass function exists. All right. Now, this has two values. The comparison theorem, first of all, is a mechanism to prove this result, that this implies this. But I should have said this is super useful on its own. Because here, to get this inequality, you have to do all sorts of crazy things to get crude bounds. Well, here, often, you don't. G doesn't have to be B times the indicator function of S or anything like that. And so you immediately get from this, under the unit chain conditions and all of that, for example, pi of F is less than or equal to pi of G. Just from our previous arguments. I mean, it's not completely obvious, but from the representation of pi, basically sticking an x dot here, right, and then summing up to tau x dot. Remember that mean cost along a cycle is how we represented the invariant probability measure. So by sticking x equals x bullet everywhere here, you can immediately infer that that's true. And so this gives you a lot more flexibility in terms of getting bounds, performance bounds.
Okay.
Yeah. Okay. Yeah. So that's it. So we have different uses. And I was going to try to come up with a homework assignment to illustrate that, and you guys, I just can't. I'd have you working night and day in homework, so I decided not to. Okay. So about converse theorems, I'm gonna help you with the homework. I'm only going to give you one converse theorem, but it leads to others as well. The only trick to get a converse theorem is this wonderful little representation. So recall this really strange thing. You'd ask, why on earth would, not just myself, you look in textbooks and Markov chains, they introduce this stopping time here, sigma s and tau s, and the only difference is here you're looking at all k, the first hitting times s, so you're minimizing over k equal to 0, and here k equal to 1. Well, I'm finally going to tell you why they have two symbols, and here it is. And so I'm basically doing one of the homework problems for you right now. The lemma I need is that if I take the shift operator, just simple shift by 1, I'll remind you what that means, and I look at a total cost, that's actually equal to Well, I'm shifting by 1. So you can imagine I'm no longer summing from 0 anymore, because everything gets shifted. I'll make this precise. So it's from k equals 1, but then it's not sigma s anymore, and we'll see why. So this little lemma, which I will prove, combined with the Markov property, not the strong Markov property, the Markov property written in this pretty way that I've mentioned before. Remember the Markov property, the expectation of theta to the 1h given f1. I'll put an n there, make it general. Thank you. So this was this beautiful result that I explained to you all. I put a little x there, it doesn't make any difference. For any n, if I take a random variable h, I hit it by the shift operator, which I will remind you what that means in a moment, and take the conditional expectation up to time n, that's the same as taking the expectation of this random variable h with a random initial condition. All right? Now, so this is definitely something in your flashcards for the exam. You need to know this representation of the Markov property. So, so why is this true? Well, the only way to prove these results is to go back to the basics. So what the hell do I mean by the shift operator? And how do I represent this object? This is my h, right? How do I represent h as a function of omega, right? Where xk is a function of omega, and it's just equal to omega k in this context, because we just make things simple and just look at sample space. All right? So let's do it. So you all know what I'm trying to get at? Okay. And in the end, I want to be able to go and show you that if this is finite valued, then we get a solution to this. Cool. So let's write it down. So what is this? So I'm calling h So the first step in all these things is to avoid the random sum. So basically, we're summing over all k for which k is less than or equal to sigma s. So you stick in an indicator function. All right, so instead of having a random sum, which is confusing, I now have a deterministic sum. It's the sum over all k, but I have this logic function that I throw away the term here if k is bigger than sigma s. All right? And then we can write this down as a summation k equals 0 to infinity of hk. Let's just call it that. This is hk.
Greater than k greater than equal to sigma.
Think so? Take a look. I'm looking at k equals 0, 1, 2, 3 up to sigma s, but when I get to sigma s plus 1, dead. Yep. No, don't worry, because it's, yep. So I'll just define this to be hk. So hk of omega. So let's get the omegas in there, because remember, xk of omega equals omega k. Let's just put those in. It's this term, so it's c of omega k. And that's too abstract looking. This says that I'm not in S. Sigma s is greater than or equal to k, so I'm not in S when? I'm not in S at time 0, not in S at time 1, and so forth. And how far do I go? Sigma s is greater than or equal to k, so it could be k. So I could be in S at time k. but I'm definitely not in S strictly before time k. Okay, go back and look at the definition. You know, sigma s is the minimum of a k greater equal to 0, such that xk is in S. So that little indicator function here is identical to that. Because it's saying that sigma s is greater than or equal to k, doesn't say anything about time k at all. It just says that I'm not in S at any time preceding k. That's all it says. All right, and then what happens when I hit this by a shift operator? See, now, oh shit. I was trying to write this all in terms of omegas. I remember whenever I write xk, it's just omega k, it's the same thing. It's just that the shift operator is defined on sequences. And so now I've got something which is a function, explicit function of omega, and hitting this by theta 1, the shift operator, just means every time you see a k, you add 1. Right? The shift operator is just a function on sequences. So whenever you see it, you go through and you look at where all the omegas appear, and you just move them by 1. That's all you're doing. You say, well, why did I move those? Well, those aren't functions of omega. There's an omega j plus 1. All right? The thing is, it's so trivial, yet so valuable. This stupid strong Markov property, or Markov property, that's all it is the notation makes things so cool. All right, so now we're done. All right, so we're done because what's theta 1h?
Maybe you should change that.
Oh, yes, thank you.
The recording.
Okay, so I take my random variable h, I hit it by the shift operator, and you see, again, this was some function of infinite sequences omega, right? And you can say, can I move the shift inside the sum? Well, of course you can. All I'm doing is I'm taking every omega and moving it over by 1. You know, it's just, you know, again, I'll write it again. Theta to the 1h, evaluated omega, is nothing but h of omega 1, omega 2, dot, 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 dot. You just, you know, this is h was a function of omega, and you're just shifting the string. You're delaying the string. So, so of course I can go through and shift each of the HKs. And that is just given by this thing here. And I'm going to go back to going to x's because I want to unravel what I just did. Xk is the same as omega k. It's the same thing. It's just, I only switched to omegas to emphasize the fact that the shift operates on the omega space. And this, you know. All right. And then I've got this indicator functions. There's a j there. It's j 0 to k minus 1. All right, so you see we're getting something nice. You can see I'm going from 0 to infinity, and that got shifted by 1. That looks pretty promising, because that's what I'm trying to do. I'm trying to say I'm summing from 1. All right, and now you see that the xj plus 1 says I'm not thinking about when j is 0, that's x1. So I have no restrictions on the first time. So this whole thing is just exactly what, I mean, what is it? I'll write it down. So it's putting restrictions on j plus 1 can be 1 all the way up to k. And so that's a condition for tau. So it's k plus 1 is less than equal to tau s. And that deserves a big happy face, QED. So that's what I claimed. That's this. Just by a change of variables, replace k plus 1 by n or whatever. Okay? All right, so there's a homework problem where you're asked to do something similar. And yes, thank you. Thank you. The homework asks you to do something very similar. Just go through the same steps. You're going to define an HK and fool around with it and get it. All right. So you're either completely lost or it's completely trivial. I wish that one of you that was lost would tell me why you're lost. You happy? Okay, so here's a converse theorem.
A little lost. From that step, indicator of j plus 1, not an s. So how do you get that k plus 1 less than equal to tau s?
Well, that's what this says. Now this is saying,
No, you're not in.
this is the same as this. And here's why. It says that, I mean, it really would help a lot if I made a change of variable, called that m, say, and said 1 less than equal to m, less than equal to k.
Oh, so yeah, so it's m less than equal to tau s, right? Indicator of less than.
No, if j is 0, then m is 1. And if j is k minus 1, then m is k. So this is correct. Okay. So it would help to make a change of variable. And the point is I'm putting restrictions on the process. I'm saying it can't be an S at times m equals 1, 2, 3, up to k. Up to k. And so that's why it says that tau s, since I wasn't an S at those times, tau s must be greater than equal to k plus 1. Yeah. I mean, look at the definition of tau s. Yep.
So I have a question. So since k is starting at 0, so is that just all times in the past before we start looking at k?
No, we're always starting at time 0. Well, not always, but so far in this course, we've never looked at negative times.
Okay, so then what would the j be?
Where?
So you're saying up to time k minus 1, and we're starting k at 0 over here.
Oh, good point. Oh, yeah, so in the special case, good point. Yeah, what happens in the special case where it doesn't make any sense? So if k is 0, then there's no restriction. Yeah, if k is 0, then this becomes a null set,
Okay.
and you just ignore it. Yeah, it's just yeah. That's a good point. Yeah. Okay. Yeah, that's good questions. So going back to the context before, let's suppose that it's the exact same setting as V3, and I've got a function f which is greater or equal to 1, and somebody told me that this thing is uniformly bounded on the set S. So like the cost over, the mean cost over a trajectory starting from S and ending at S is finite, uniformly bounded. Then I can go through and I can just use my machine here. All right, so that's what you'll find in the handout. It's called V sub f, just like this. And then I can apply this lemma. Okay. Oh yeah, and finite. Of course, I want it to be finite everywhere. Yeah, define this. Who cares? I don't even have to. I won't even say that. In fact, all I need is this. You'll see. Maybe this is infinity all over the place, but it's finite and uniformly bounded on S. Okay, I can still play with my magic. So given this lemma, I can now use the Markov property. So. How do I say this? So, just get a load of this. P V F at X is equal to the expectation X of VF at time x1. All right, it's expanding this out. All right, so that's a thing that you're supposed to read every time before you go to bed. And the sub x just means conditional expectations. But that when it's lucky I went through slowly here because this looks crazy. That's a function of x, but sticking in x1 is something we saw with the Markov property. All right, now. And thank you for the pens. I could not have done this. We could call it H. Want to call it H? So I have to write down that monster? Yeah. All right. H was defined somewhere, right there. We define it as H in the proof. You can keep it as H now. And we know now by the Markov property that this is just that. So it's the expectation of theta to the 1h given F1 I just went backwards. This is equal to this. There's nothing, there's not a single bit of brains in anything I'm doing. It's just notation. Okay, this is this. It's just a reinterpretation. And then that we said is that. Okay. All right, so from here to here, I just use the lemma. And now I can use the tower property or the smoothing property. Oh, and there's no minus one there, sorry. Yeah. It's just tau s. Okay, so that's what I call smoothing. And engineers seem to call the tower property recently. It used to always be called smoothing. And this is the lemma. And this is the Markov property. So can anybody tell me about this? So remember, these guys are the same most of the time, right? If I don't start in S, then the k equals 0 doesn't matter. Sigma s and tau s are the same thing if I don't start in S. So this thing here, I've run out of room. Do you mind if I just go dot, dot, dot here? It's equal to, with two cases, if I'm not in S, it's just, I can replace the tau s by a sigma s, and I'm losing the first term. And I'll just write it down. It's v of f of x minus, oh, I go, it's c, damn you, it's f. I go, it's c here and f there, I'm sorry. All right, f is my weighting function bigger than 1, c is my cost function. Anyway, so this is true for any function. C was not something special. So if I'm not in S, then basically I get exactly the sum that is in the definition of VF, but I lose the first term. And if I am in X, well, it's some horrible monster. But let's give this a name. I don't know. I sum from 0 to tau s, so I made this even bigger. So within S, it's bounded. And so you can go through and be done with it because S is a finite set. And so, in fact, if X is an S, in fact, actually, I should have stopped here. What is V if X is an S? Yeah. So if we start in S, and sigma S is just 0, so we just plug in this guy. And so I say it's less than equal to BF, but BF is actually equal to right? So if I'm in S, I can write down VF of X minus F of X, that's 0. Okay? And then I've got this sum here, starting in S, all I know is it's bounded. And I'm just giving it a name, I'm calling that BF. That's condition V3. Okay, so conclusion, Converse theorem. There it is. All right. Now going back to that thing that I forgot to say, oh, that's right, I need to assume this is finite everywhere. Well, it turns out I don't. It turns out that once you show this inequality, and once you show that, we assume that this is bounded on S, it's actually finite valued on the communicating class. You can show you get finiteness for free, but that's, that's, who cares? mainly, the whole point of this is just to say that looking for V3 is not a waste of time. If the invariant PMF exists, a solution must exist. So it's not like some small fraction of Markov chains for which you can find the solution. Right? And also, I want you to play around with these. It's a good exercise to play around with these shift operators. All right, questions? Yeah.
We proved using that VF as our Lyapunov function that V3 holds.
That's what we see right here. So we see PV is V minus F if X is not an S, and it's V minus F plus a constant X in S. If you go back and look at V3, that's the definition. And BF is this constant. So it's pretty awesome. And that's exactly the style of converse theorems you find in deterministic control theory. You look at the total cost, and that's a Lyapunov function. It's just exactly the same.